All right, so the other part that we were mentioning earlier is this notion of sometimes divisibility doesn't always work. In this case, it occasionally fires off some remainder. And that's exactly what the division algorithm is all about, is that if you start with some number a and you have some nice little divisor in this case, which I'm going to call a d, what ends up happening is that it's always going to fire off a nice quotient q as well as a remainder r in such a way that you're going to get this particular representation. Which if you go back a couple slides, that's exactly the case that I had with the 3 and the 26. If I took the 26, divided it by the 3, I get a quotient of 8 with a remainder of 2. So that's exactly that representation. Same thing for the 120. If I take 120, divide it by 49, I get a quotient of 2 and a remainder of 22. So in general, that representation is a very slick and useful way to represent this number. In terms of this thing, that's not quite a divisor, but I get a little bit of remainder term afterwards. So that's the division algorithm. There are some fancy ways to represent some of these pieces. That quotient q is often just created by taking a divided by d. So sometimes we use this notation that says a div d. That one's not very common. The one that does occur all over the place is the remainder, which in this case is going to be connected to the modulus. The idea is that I'm going to get this quotient q and a remainder r, and the r is often represented as this a mod d. So some of you may have seen this piece of terminology before. A lot of programming languages have this pre-built in. In Math 201 or Intro to Discrete, we talk about this all over the place, but it's a fundamental concept that we're going to use a lot. So it's worth, like I said, stressing again. There are some actual really nice ways to compute these things. So the quotient is done by taking exactly the quotient you would expect. So take that number a divided by d, and in this case, I want to take some integer version of this thing, and to achieve that integer, I'm going to take the floor of that answer. So the floor is essentially this really lazy way of rounding, just round down. So things like 4.1 round down to a 4, 3.9 rounds down to a 3, negative 3.9 then rounds down to a negative 4. So that's the one that is slightly different than the integer command in that that might have rounded up to a negative 3, but in this case, I properly want to round down to the negative 4. What ends up happening is that if you replace this a over d floored into this expression that we have right here and solve for r, we actually get a representation for what this modulus is supposed to be. You take the original number a, you subtract off this divisor d, and then multiply it by this new little fancy quotient. So it's kind of a test to see what's going on. If I were to take the number 26 divided by 3, so I get 26 over 3, which is 8.6 repeating. That floored turns into an 8. And then my r value is going to turn into a 26 minus 3 times that new quotient 8, which fires off a 2. Which is to say that this number 26 is going to be that divisor 3 multiplied by my quotient, which is the 8, plus that little remainder of 2. So what you can see in this case is that 26 modulo 2, or modulo 3, I should say, is going to turn into that number 2. And that's going to become a really important concept as we begin to move forward. This modulus is going to store a whole bunch of very useful information. What's nice about this is that we can flip this to the negative side. So if I take negative 26 and divide it by 3, and this is the one that some people often have struggles with, is that they mess up the negative sign a little bit. And this is where that floor command is very fundamental. So if I take the negative 26 and divide it by 3, it's again going to point out or kick out this 8.66 repeating, but it now has a negative sign out in front. So if you take the floor of this expression, it then fires off a negative 9. So if you now compute that remainder value, you're going to get the a, which is negative 26, minus 3 multiplied by a negative 9. So those two things are going to multiply to make a positive 27, kicking out a remainder of 1. And what's nice about this is that this construction that we have right here is guaranteed to give you a positive r, which is nice, or at least a non-negative r, which is what I want to have happen in my division algorithm. There's one of these subtle important steps that says, hey, this r value should be between 0 and d. I'm allowed to be 0 if I know that it divides nicely, but in this case, it's going to be something between 0 and d. Later on, we're going to talk about things that might actually kick out negative numbers, but for right now, we don't want to think about that. All right, so if you're interested, there's another example running through with 100 and negative 100 and the divisor of 15. I'll leave that as something you can just peek at your own leisure, I guess. Exact same process, just another example. What we're going to look at, though, in this case, we're going to take a whole bunch of numbers and try to divide them by 5. So in this case, if I take 14 and divide it by 5, I want to think about what the quotient's going to be, and then I want to think about what the remainder is going to be. And sometimes you can just kind of go right from the get-go. The idea is that 14, well, divided by 5, is I know that it goes in there 2 times, because 2 times 5 is 10, leaving me a nice little remainder of 4. So hooray! All right, let's try to do 54. And maybe we'll try to use this little formula. So if I take 54 divided by 5, that's going to help create this quotient, which is 54 over 5. And if I take that, so 54 over 5 is something like 10.8-ish, I guess. And flooring that turns into a 10. So my modulus in this case is going to be an r, which is going to be that original number of 54, minus, so I'm going to think about what I'm dividing by in this case. I'm dividing by a 5, and I'm going to pull that 10. So 54 minus 5 times 10, which is an answer of 4. And maybe you saw right from the beginning, but that's okay. The idea is that 54 is going to be this 5 times 10 with a remainder of 4. All right, let's do the negative one. So if I have n being this negative 36, my quotient is going to be negative 36, that divided by a 5. And if I compute negative 36 over a 5, it's something like a negative 7.2, which floored is going to turn into a negative 8. So my r value is then a negative 36 minus my quotient, or my divisor 5, and then my quotient of negative 8. So if you compute this, you see that there's that double negative occurring, so that's going to turn into a positive 40, with the negative 36, again, is going to turn into a 4. So in this case, you see that negative 36 is going to equal 5 multiplied by negative 8, and then plus that remainder of a 4. What's neat about all of these is that in all 3, in this case actually 4 if you did it with 179, you end up seeing that we end up with a remainder of 4. Which in this case, we're going to say that these 4 numbers are all congruent to 4 modulo 5. Is that under division by 5, they all have the exact same remainder. In this case, they all have a remainder of 4. And that actually leads us to our next definition. It's this notion of congruence modulo m. So we're going to say that 2 numbers, a and b, are actually congruent modulo m if they have this exact same remainder underneath this division by m. In this case, we're going to use this notation that says a is congruent to b modulo m to actually indicate that these 2 things are congruent. In this case, that little number m is going to be referred to as the modulus, which becomes a nice thing that we're going to work with. One of the key facts that we kind of push under the rug but becomes pretty important is that if we have a remainder of 0, well, what that tells me is that I know some number divides another number. So if we run this argument of taking, if I have some a and if I divide it by b, I'm going to get some quotient, and let's say there's no remainder in that case. So that's going to say that a modulo b is 0. Well, in this case, you can then see that b divides a, which is exactly what this proposition says, is that those 2 things are saying the exact same thing, is that b divides a is the same thing as a mod b is 0. I typically like to work in the world of moduli. I think it's a little bit easier than thinking about all these divisibility things, is that it's easy to test if something modulo another number is 0. It's also way easier to code. You don't have to go looking for horrible divisors and things like that. You can just do one line that says, hey, is a mod b 0? If so, then I know it's divisible, and I can go from there. Else I have to go do some other random things. With that, you also have an alternative definition for this congruence modulo m, and I'm just placing it here because different textbooks will sometimes use different definitions. So another way to say congruent modulo m is if their difference, a minus b, is divisible by m. And you can see that using this little proposition up above, those 2 things are saying the exact same. The idea is that this and this are identical. So we'll probably leave it at that for this video. I know it got a little bit long, but it was kind of a good amount of early definitions and things like that. In the next bit, we're going to be talking about greatest common divisors and then leading into the Euclidean algorithm.